Yeah, I need to check.
The temperature goes to zero when you get immense, which is a property of the spectrum channel.
Oh.
So this problem is wait 1 year to clean up.
Cirella che c'è un...
Okay. Okay, so we can start the second morning session, and the first talk will be by Gregory E. Astrakharchik. So please, you have 25 minutes plus 5.
Okay, thank you. So I'd like to present the results I brought together with Jordi Boronat from Polytechnic University of Catalonia, Barcelona, and then also from the same university. And other collaborators, Yuri Lozovic and his physics student Alexei Golomeda from Russia, Institute of Spectroscopy. And we wanted to study the properties of two-component Coulomb gas and to test explicitly the applicability of the bosonic description in terms of excitons interacting with S-wave scattering length. So our goals are following. We want to study a system of positive and negative charges interacting with Coulomb interaction, and do non-perturbative simulations by using Monte Carlo techniques. In this case, this would be a fixed node diffusion Monte Carlo method, in order to find the ground state properties, such as the equation of state and the correlation functions. We want to see how the excitons are formed in the system of fermions, and to test the possibility of describing the equation of state, in low density, in terms of delta interacting bosons, the excitons, and see if we can use the Gross-Pitayevsky equation, and if it's possible to go beyond mean field. So in the energy, this would correspond to having Lippmann-Young terms. Because here the question is if, let's say, what would the correction might be Lippmann-Young, let's say bosonic, so the correction would be density to the power 1/2, or otherwise it might have structure of fermionic corrections in terms of Fermi momentum, which would mean that it should go like density to 1/3. And we will calculate the exciton S-wave scattering length by solving explicitly a 4-body problem. But sort of true motivation was lectures by Monique Combiston, which I attended in 2008, and she has a number of papers where she is making very strong and maybe potentially destabilizing claims for the communities, and that the effective bosonic Hamiltonian for excitons, extensively quoted up to now, cannot be correct because it is not emission. The oversight physically originates from the intrinsic difficulty of properly defined electron-hole interaction between excitons when dealing with exchange terms. The effective bosonic Hamiltonian must contain purely fermionic terms of the same order as Coulomb terms. So essentially what she says that the Gross-Pitayevsky, or let's say the bosonic Hamiltonians, cannot be applied to excitons because the Coulomb interaction, which is long range, introduces the contributions which are of the same order. And okay, so this is something which we wanted to address. And the structure of the talk will be followed. So first of all, I will consider a 4-body problem. So having 2 positive particles, 2 negative particles, and we'll calculate the exciton S-wave scattering length. Once we know it from this 4-body problem, we will switch to properties of a homogeneous gas, And then we will find the equation of state of a gas at a given density, and then we'll check if we can use the mean field Gross-Pitevsky equation to describe the energy, and we'll test the beyond mean field contributions. Then we'll also calculate the condensate fraction of excitons, and also we'll compare it with the Bogoliubov theorem. Okay, so just to consider the model Hamiltonian trap. Actually, here we already simplified a bit the problem. Okay, let me explain it better. So we have, let's say, electrons, negative charges. We have the kinetic energy. If we have a trap, then there is also trapping potential. And we have Ne electrons and NH holes. So this is the kinetic energy of holes, again the trapping potential. And then we have three interactions, let's say reduction interaction, which would be repulsion between electrons, repulsion between holes, and attraction between electrons and holes. We consider a three-dimensional system, so there are no layers. The simplifications are that we consider the same mass for hole and for electron, although in principle hole should be heavier. And also we ignore the spin degrees of freedom, in the sense that for electrons we say that they are completely polarized, and the same for holes. Okay, those simplifications probably will not permit us to compare directly to some possible experiments, but anyway, the problem is already present in this Hamiltonian sense that the excitons will be formed here, and then we will check if it's possible to use the bosonic description for such a system. Okay. Also, we consider charge neutral system, so number of electrons will be equal to the number of holes. Okay, if we consider a trapped system, it is convenient to use the units of a harmonic oscillator, which means that energies will be measured in the units of spacing of a harmonic oscillator, and all the distances will be measured in the length of the oscillator length. Well, it's easy to check that in the Hamiltonian. Essentially, we have a dimensionless parameter which can be introduced like the Bohr radius measured in the units of the oscillator length. So I'll call it A naught theta. And here we have also the, well, in principle, other parameters would be a number of electrons and number of holes.
What's the definition of AX? What's the definition of the interaction parameter?
Yeah, so this is exactly the Bohr radius measured in units of the oscillator length. So this is A node divided by A harmonic oscillator length.
That one?
Yeah.
The AX?
Yes, exactly. So this is the one which I have here. So it's the physical meaning is the Bohr radius. Or let's say, on the sides of the exciton equation. Okay. Okay, so our goal would be to solve the four-body problem, but we start with first from two particles, from one hole and one electron. So this is two-body problem, and this problem can be at least resolved by separating the center of mass motion and enough with the contribution from the center of mass motion, which doesn't depend on the interaction, which will be perhaps in bar omega, and then with differential equation for the relative motion, which essentially has the kinetic energy, I have the trap, and then I have the interaction with the, let's say, center of the trap of the 1 over r of the attractive Coulomb type. And here, of course, it's possible to solve this differential equation and get the energies. So we get the contribution to the relative energy and the center of mass. So we know what is the total energy. We solve it on a grid, and then we see how this binding energy, which is negative because here electron and hole form a bound state, essentially an exciton. Also when the size of exciton becomes smaller, the binding energy becomes larger. Also, here we already checked that if we use the Monte Carlo method to solve the two-body problem, it works properly in the sense that we get the same energy. So here, so far, we know what is the energy of two particles. Then we will solve the four-body problem. This time already using Monte Carlo method. And then what we want to do is to obtain what is the relative energy corresponding to interaction between excitons. So the idea is quite simple in the sense that we have, say, for particles, we have a positive, we have a negative particle, we have a positive and negative. And then, we will be in the regime when excitons are formed. So there's essentially two composite objects, and then the size of Bohr radii, while the distance might be quite large, and then we put a trap on the top of it. And then we find the energy of this system, and then we want to describe the same system as a sum of two point-like bosons. So we have only two particles, again in the trap. And then we just want to map one problem on the other. And from this mapping get the S-wave scattering length. In the sense that if we have the description in terms of two bosons, two bosonic particles in trap can be solved exactly, Bush, Rojevsky, and others. And energy of two bosons can be calculated for any S-wave scattering length between two bosons. Essentially, we have a method which is kinetic energy, the harmonic wave, and then interaction between bosons is a delta interaction. So it's point-like with some unknown so far S-wave scattering length between exciton and exciton. So AEE is the S-wave scattering length between two excitons. If we obtain what is the relative energy of the interaction by the trick which I'm doing here, essentially I calculate the energy for four particles by using Monte Carlo method. Then I subtract the binding energy of each exciton, which again I know. Then actually I have also the center of mass motion, which is real. So far I am able to localize what is the energy corresponding to interaction between two excitons. Then this energy I want to describe in terms of bosons. And then essentially I need just to compare what is the energy that I have in the system and what would be the S-wave scattering length in corresponding bosons interacting with delta interaction. And in this way it's possible to extract the exciton-exciton S-wave scattering length. Here I am changing the Bohr radii. And in principle, the trap is needed here just to make the particles not fly apart. So somehow anyway we are interested in the limit when the trap is very shallow or disappears. So when this ratio goes to 0, and then in this way we would be able to get the S-wave scattering length of homogeneous system, and then we get something which is compatible with let's say 3 in terms of Bohr radius. So here the first result is that the S-wave scattering length is 3 Bohr radius. Okay. Once we know what is the S-wave scattering length, we deal with many body problem. So now we remove the trap, essentially, and here in this case, I've done the same as before without the trap. Here it's convenient to use the atomic units. So we measure the distances in units of the Bohr radii and express the energies in Hartree. And then the dimension is Hamiltonian. I can introduce in such a way that doesn't contain any dimensionless parameter, but then I will have the dimensionless density, which would be just the number of particles per volume times the Bohr radii cube. So I call it gas parameter, like in period weakly interacting, say, Bose gas, or well, another way is to introduce RS parameter, which is actually, well, again related to the same quantity. So finally I will give the expressions in both results. Then we use fixed mode diffusion Monte Carlo method. So I actually will not give much details on that, but we use a Gaussian wave function which has a proper symmetry under exchange of two electrons or under exchange of two holes. Essentially, the wave function must change the sign. And in comparison with BCS-BC calculations for the Fermi gases, this symmetry would correspond to superfluid structure. Here, as the orbital to the determinant, we use the lowest two-body electron bound state, which will give us the energy which will be minus 1/4 of R3, and the orbital is essentially just exponentially decaying function. Okay, so when we will calculate the equation of state, we would like to compare it with the expansion at small density, which would mean that if we have exciton size which is small compared to the interparticle distance, we would like to describe the system in terms of Bose-Hamiltonian, so that the main contribution would be the binding energy of, well, each exciton, but okay, it's something which doesn't depend on the density, so the compressibility doesn't feel it. And this is, okay, this would be just minus 1/4 of R3. And then the interesting contribution, which will depend on the density, will be the mean field Gauss-Vitebsky term, which says that, say, energy per particle is proportional to the density, or the chemical potential proportional to the density. And then maybe we'll have Lippmann-Young Bjorn field correction, which would say that the next correction in the density would scale like density to one half. Although, as we are dealing with composite bosons, here actually the number of excitons would be twice smaller, and each exciton has a mass of 2m, and the S-wave scattering length is the one we obtained before. Okay, so this is the result for the energy, and this is the density. So this is small density. This okay, here it goes in the direction of a large density. RS parameter would be inverse, essentially. And this is the energy per particle in units of R3. When the density is very small, we see that the energy approaches to the to the binding energy of an exciton. Then apply the mean field Gauss-Vitebsky correction, which goes above. Here probably, okay, we don't have enough resolution to see it. But definitely, if we add the beyond mean field Lippmann-Young term, actually it works pretty nicely. So somehow this gives a confirmation that actually, at least for the energy, it is possible to use the bosonic description. And furthermore, it goes not only on the mean field level, but also the Bogoliubov theory, or the, let's say, corrections describe properly the contributions to the energy. Also, it's quite interesting to know that the density up to which this correction works, okay, which is more or less, let's say, 2 × 10⁻³ would correspond to the, let's say, to the bosonic density even larger, 3 × 10⁻². So here the beyond mean field correction is applicable even for larger densities than in weakly interacting Bose gas. So one possibility of that is that, or description, well, explanation for that here the energy doesn't depend very strongly on the density, in the sense that not that strongly as for a Bose gas which needs to crystallize for densities of the Rhodel plan, while here we will end up with ideal thermic gas, which has, well, somehow not that large density. Okay. In the regime of large density, what happens is that the interaction energy is small compared to the kinetic energy, so we can compare to the energy of two ideal thermic gases. And actually, after Biagio theorem. He gave me quite nice mean-field correction to it, which actually was already present in the book by Peter Valeshko, which we also test. And the complementary part of the energy for going to much larger densities. And when the density is large, I plot the ideal thermic gas result, so it's quite odd. But if I add let's say, the mean field correction to the ideal thermic gas, it seems to coincide quite well. And that probably we need to add some points also here. But the conclusion would be that at low densities it's possible to use perturbative Bose theory. At large densities, the thermic theory. Here, okay, in this regime will be no theory, but Monte Carlo data would provide us the result. Okay, so this is the complete energy. And maybe I'll skip it. And the last quantity which I want to consider would be the condensate fraction of excitons. Well, in the sense that if we are dealing with fermions, so there is no condensate, and that in the one body density matrix there is decay to zero for long off-diagonal distances. So we need to consider a two-body density matrix which would correspond to essentially taking the electron-hole pair out from one place and then inserting it in some other place. And for large distances, if there is a condensate of excitons, this quantity should go to constant. And then this we'll compare this this constant with the bosonic expression for the condensate fraction, and that for Gross-Pitevsky we have all particles which are fully condensed, and this is the quantum depletion of it's essentially Yupan-Yang terms. Instead, if you have ideal thermic gas at large densities, the condensate fraction must be zero. And this is the result that we get for the condensate fraction, and you see that this decreases smoothly from 1 to somehow small values. And indeed, for quite low densities, the Bogoliubov theory predicts the correct result. In this sense, again, it's interesting to see that the Bogoliubov theory works here and describes not only the energy but also the condensate fraction. So here actually the question would be if it's possible to have the prediction for the condensate fraction for weakly interacting fermions. I don't know, maybe say your group here in Mirina can tell me the results. So let's say if the density is large, and then I have finally ideal thermic gases, and here I have, let's say, weakly interacting Fermi gases, then what would be the condensate fraction of excitons of pairs? Because if you have it, it would be very nice to compare with it. Well, with this I switch to conclusions. What we did, we considered the electron-hole plasma in a three-dimensional system. We made a fixed node diffusion Monte Carlo calculation to find the ground state properties. We checked how the electron-hole pairs of excitons are formed. From the four-body problem, we found what is the S-wave scattering length, and this is 3 units of radii. And we found that it's possible to use the bosonic description for the energy and correlation functions. And the first correction is the mean field correction given by the Gross-Pitevsky equation, and the Li-Huang-Yang terms of the Bogoliubov theory works pretty nicely. So the final conclusion that still that it's possible to describe with bosonic Hamiltonian, which probably is this should be. Okay, thank you very much for your attention.
Thank you a lot. So we have time for questions, please. One here.
When you calculate the condensate fraction of the pairs, basically the two-body density matrix depends on 4 distances, but one is irrelevant because of translation invariance. Then the 3 remaining, one could be the distance between the pairs, but then you still have the size of the pairs. Do you put
No, I'm sort of integrated this out, in the sense that for any size of this pair, actually, I'm still displacing it for some distance. So this is the only parameter which I have, and then I'm integrating out this size. So for me, it is not relevant. And in this distance, essentially, I'm interested only in the absolute value, how much I displaced it. So finally, I'm ending up with an expression which depends only on one parameter, so how far I displaced it.
Okay, so but when you go to the ideal Fermi gas limit, let's say, then I guess at least the variance should explode because you are weighting I mean, the pairs become very, very large. So it's difficult.
No, but this is a different thing. One thing is the size of the pair, and the second is what is the value of my wave function when I killed it here and when I put it here. And for fermions, when I put it here, it's essentially 0, or okay, it's very small. So on one side, okay, it's still more difficult to consider the fermionic regime. Okay, what is it? But I guess for yeah, here for example, the error bar is quite large. But this is mainly due to the fact that the density is very large. And then again, for me, it's very difficult to do the calculation because also I have very strong finite size effects. But somehow I'm pretty sure that it must go to 0.
Okay, Alan?
I guess you must have thought about doing this calculation with periodic boundary conditions.
Yeah, okay, maybe I didn't explain it very well, but in the beginning we considered 4 particles in a trap, so there were no periodic boundary conditions. But then when we consider a homogeneous system, actually we do use periodic boundary conditions to have a finite density. So actually we use them.
Okay.
Alexei?
And so, if in the calculations in the trap, what is the meaning of this asymptotics to get the condensate fraction, not the correlation function, or you are doing this without the?
No. I can calculate the condensate fraction only in a homogeneous system. In trap, it has. Okay, in principle, I can use the natural orbital expansion, but the problem is somehow different.
I thought that you are calculating this everything in the trap, so that was the question.
So in the trap, I'm doing calculation only for 4 particles in order to get the S-phase scattering. And after that, I eliminate the trap, and then I'm working at given density, so everything is plotted in terms of the density. So there is no trap anymore.
So, just another, Biagio?
So essentially, you have disproved the statement by Monique on this call that. Now, I just want to ask you: has she given some explicit expression for the corrections due to
that's the problem, because I don't. What she says that I don't know. For example, one way out, or I don't know, possible is that, for example, for some green functions, the expression that she gets are different, but she doesn't provide an explicit expression for the energy or for the correlation function or some observable which I can compare and say that she's wrong and this is right. What I claim is that for the energy and for the correlation functions, the bosonic description works.
Okay.
Maybe there are some other questions?
Yeah.
Just, have you tried to determine the scattering length using the bosonic energy and leaving the scattering length as a meter fixed? So if you take into account that your curve is correct with V1, you can optimize the scattering length.
Yeah, exactly.
Is that compatible with the calculation?
Yes. Well, yeah, you can see it also here. Let's say I can use, let's say, my S-phase scattering, which is 3 units. It's already fixed from the body calculation, and this will give me this green line. Otherwise, I can use it as a fitting parameter, and then, okay, in order to fit well, it should pass again from those points. So actually, it is compatible. It gives me the same number. So there are two ways to define the S-phase scattering in both concepts.
That's nice.
Okay.
You have some uncertainty.
A very last quick question by Ellen, and then we
Can
can
I
move on.
say, you know, these excitons should have long-range dipole interactions in addition to short-range interactions. Are you saying that they don't matter at all?
Probably to some extent, yes. Because when I measure the energy, I see that Bose-Einstein description in terms of the only short-range interaction potential is already enough. For dipoles, actually, I mean, in my situation, dipoles can change their rotation orientation. So probably the average contribution would be anyway 0. But my claim is yes, they are not important.
Okay, now we need to go on. Thanks again to the speaker and for hosting this lecture. Thank you very much. Now I call David Nilsson.